Hello my students, your physics teacher Hassan Darwish with you. This is video 4 about the atom. In this video, I am going to explain the emission and absorption spectrum of the hydrogen atom. Remember, in video 3, we can calculate the set of values or set of allowed values of energy of the hydrogen atom. You remember Bohr's calculation here, applying Bohr's formula from this formula, right? Now let's find the emission spectrum of the hydrogen atom. In reality, here is a hydrogen lamp, glowing hydrogen lamp. And here in this figure represents the visible spectrum of the hydrogen atom. Let me use the magnifier. Look at the spectrum. You see the red color, blue. Here there is a color between indigo and violet. This is called indigo, between blue and violet, and this is violet color. Okay? This is the spectrum of the hydrogen lamp. You may use a single slit diffraction pattern or any spectrometer to obtain this spectrum. Now, Mr. Balmer, in order to calculate the wavelengths of each color, obtained an empirical formula, means a formula by trial and error, to calculate lambda. Now, this formula is given as 1 over lambda equals a certain constant R, called what? Rydberg constant, into 1 over 2 squared minus 1 over n squared. Why is this? We don't know why. He obtained it by trial and error. Okay? But this number, lambda, must always be positive number. So n must be greater than 2. So n equals 3, 4, 5, up to infinity. Okay? Let's make a direct example to calculate the wavelengths. Calculate the wavelengths of the series limit. Series limit. We mean by series limit the longest and the shortest lambda of Balmer's series. Let me go here to Balmer. Here, for example, this is lambda, right? Okay. In this region, we obtain what we call infrared. You start here infrared or microwave. Here in this region, you obtain the frequency, because lambda and frequency, here is a frequency, upward, lambda increases, opposite to the frequency. You obtain here what we call ultraviolet. We need in the example the longest lambda and the shortest lambda of Balmer. Okay? Now look at this rule. Longest lambda means what? So longest lambda means what in your opinion? Means 1 over lambda smallest, right? Smallest. To have smallest 1 over lambda, R is constant, means this number is smallest, right? So 1 over 2 squared minus 1 over n squared is smallest. If this is smallest, means minus 1 over n squared is what? Biggest, right? Because there is minus here. Means 1 over n squared biggest. But 1 over n squared biggest implies n squared what? Because inversely proportional. Smallest number. Right? What is the smallest value of n? N equal what? 3. Implies n equal 3. So if you do the calculation, means replace here 3 and replace the value of r, you get lambda equal 656. Then you obtain nanometer. You obtain the wavelength of this color. Okay? We need now shortest lambda. So the opposite way. Shortest lambda. Shortest lambda means what? Means 1 over lambda biggest, okay? Or largest if you like. One over lambda biggest here means this number is biggest, right? Means minus 1 over n squared smallest, means n squared biggest, okay? So n equal infinity. The biggest value of n is what? Infinity. Then if you do the calculation, you get lambda approximately. So lambda equal 365. 365 nanometer. But notice here 365 less than 400. Sorry. Less than 400 nanometer means 365 is in the ultraviolet range. So Balmer series starts from this wavelength up to ultraviolet value. Okay? Any problem? But later researchers discovered lines in the ultraviolet range, here it is, and infrared range. So Balmer's formula is generalized. Okay, because if you go back to this lamp, Balmer only discovered the visible range. But in reality, there exists microwave range or infrared range and ultraviolet range. That's why Balmer's formula is customized to this form. Here, if the n final equals 1, then an initial starts from 2 or 3 or 4 up to infinity. And this is called in reality Lyman series. Lyman. And all the series lie in the ultraviolet range, means not visible for us by our naked eye. For n final equal 2, here n final 2, we obtain what? This formula, which is Balmer series. So an initial must start at 3 and 4 or 5, clear, etc. Then we obtain what we call Balmer. Balmer series, which is visible and ultraviolet. If n final equals 3, then you get an initial must start at 4, 5, 6, 7, etc. up to infinity. Then we obtain what we call Paschen series. Paschen series. But this Paschen series lies in the infrared range or in the microwave range, means also not visible. So only in Balmer we have visible part and ultraviolet part. Clear? So if you go back to our lamp, here we obtain Paschen series. This is Balmer series, and here, which is also not visible, we obtained Lyman series. Okay? So we may represent this series in this diagram. Notice here, in the Lyman series, the final state of the atom is unequal to 1, the final orbit here. So the electron may jump from 2 to 1, from 3 to 1, from 4 to 1, from 5 to 1, etc. In Balmer, electron start from 3 to 2, 4 to 2, 5 to 2, etc. from to infinity. Then you get the visible and ultraviolet. With these, we do not see the emitted photon because all the photons here in this Lyman series are ultraviolet photon. Now Paschen. Paschen from 4 to 3. Notice, from 5 to 3, from 6 to 3, etc. All of them are invisible. They are infrared. Now bracket series and Fund series, etc. Bracket to unequal to 4, the final state of the atom or final position of the electron. Okay, or we may represent it in this way. Notice here in the energy level diagram, from 2 to 1, 3 to 1, 4 to 1. Don't forget, with each transition we have an emitted photon, right? So all the photons here are invisible. They are ultraviolet up to infinity. Now let's come to Balmer. 3 to 2 we obtain red. Remember in the example, from 3 to 2 we obtain the red, 656 nanometer. Now 4 to 2 you obtain the blue, the next one here. 4 to 2 you obtain this color, the blue. 5 to 2 you obtain the indigo. 6 to 2 you obtain the violet. From infinity to 2 you obtain the, as we observed in the example, 365 nanometer ultraviolet. Now Paschen, 4 to 3 or 5 to 3 or 6 to 3, etc. to infinity to 3, you obtain the series of Paschen and etc. Okay? Now absorption spectrum. Experiments showed that an atom only absorbs photon of same frequency as those which it emits during the excitation. It means what? For example, the hydrogen atom, as we have seen, emits the red photon. It absorbs the red photon. In this spectrum, you do not see yellow color, right? So this hydrogen lamp or the hydrogen atom cannot absorb the yellow light, okay? And similarly the orange light or green light. It only absorbs the photon it emits. Clear? So the energy of the absorbed photon, the same as, look here, the same as the energy of the emitted photon, but the rule is opposite. Initial minus final for emission, final minus initial for absorption. Look here, emission spectrum, absorption spectrum. Clear? We have here two close yellow color for sodium. So sodium